We spent a good deal of time on the idea of a null space. What I'm going to do in this video is introduce you to a new type of space that can be defined around a matrix. It's called a column space. Column space. And you could probably guess what it means just based on what it's called. But let's say I have some matrix A. And let's say it's an m by n matrix. So I can write my matrix A, and we've seen this multiple times. I can write it as a collection of column vectors. So this first one, second one, and I'll have n of them. How do I know that I have n of them? Because I have n columns. And each of these column vectors are going to have how many components? So v1, v2, all the way to vn. Well, this matrix has m rows, right? So each of these guys are going to have m components. So they're all members of Rm. So the column space is defined as all of the possible linear combinations of these column vectors. So the column space of A, this is my matrix A. The column space of that is all the linear combinations of these column vectors. Well, what's all of the linear combinations of a set of vectors? It's the span. It's the span of those vectors. So it's the span of vector 1, vector 2, all the way to vector n. And we've done it before when we first talked about span and subspaces. But it's pretty easy to show that the span of any set of vectors is a legitimate subspace. It definitely contains the 0 vector. If you multiply all of these guys by 0, which is a valid linear combination added up, you'll see that it contains the 0 vector. If, let's say I have some vector A that is a member of, let's say it's a member of the column space of A. That means it can be represented as some linear combination. So A is equal to, c1 times vector 1 plus c2 times vector 2, all the way to cn times vector n. Now, the question is this closed under multiplication? If I multiply A times some new, let me say I multiply it times some scalar s. I'm just picking a random letter. So s times A. Is this in my span? Well, s times A would be equal to s c1 v1 plus s c2 v2 all the way to s cn vn, which is once again just a linear combination of these column vectors. So this SA would clearly be a member of the column space of A. And then finally, to make sure it's a valid subspace, and this actually doesn't apply just to column spaces. This applies to any span. This is actually a review of what we've done in the past. We just have to make sure it's closed under addition. So let's say A is a member of our column space. Let's say B is also a member of our column space, or our span of all of these column vectors. Then B could be written as, I don't know, let me say b1 times v1 plus b2 times v2, all the way to bn times vn. And my question is A plus B a member of our span, of our column space, the span of these vectors? Well, sure. What's A plus B? A plus B is equal to c1 plus b1 times v1 plus c2 plus b2 times v2. Right? I'm just literally adding this term to that term to get that term, this term to this term to get this term. And then it goes all the way to bn plus cn times vn, which is clearly just another linear combination of these guys. So this guy is definitely within the span. So the span of, and this, what I just did, it doesn't have to be unique to a matrix. I mean, a matrix is just really just a way of writing a set of column vectors. So this applies to any span. So this is clearly a valid subspace. So the column space of A is clearly a valid subspace. Now let's think about other ways we can interpret this notion of a column space. Let's think about it in terms of, let's think of it in terms of the expression, let me get a good color. If I were to multiply let's think about this. Let's think about the set of all the values of, if I take my m by n matrix A and I multiply it by any vector x where x where x is a member of, remember, x has to be a member of Rn. It has to have n components in order for this multiplication to be well defined. So x has to be a member of Rn. Let's think about what this means. This is the set. If this says, look, I can take any member, any n component vector, and multiply it by a, and I care about all of the possible products that this could equal, all the possible values of ax, when I can pick and choose any possible x from Rn. Well, let's think about what that means. ax, if I write a like that, and if I write x like this, and let me write it a little bit better. Let me write x like this, x1, x2, all the way to xn. What is ax? Well, ax could be rewritten as x1, and we've seen this before. Ax is equal to x1 times v1 plus x2 times v2 all the way to plus xn times vn. Right? We've seen this multiple times. This comes out of our definition of matrix vector products. Now, if ax is equal to this, and I'm essentially saying that I can pick any vector x in Rn, I'm saying that I can pick all possible values of the entries here, all possible real values and all possible combinations of them. So what is this equal to? What is the set of all possible? So I could rewrite this statement here as the set of all possible x1, v1 plus x2, v2, all the way to xn, vn, where x1, x2, all the way to xn are a member of the real numbers. That's all I'm saying here. This statement is the equivalent of this. When I say that the vector x can be any member of Rn, I'm saying that its components can be any members of the real numbers. So if I just take the set of all of the, essentially, the combinations of these column vectors, where they're real numbers, where their coefficients are members of the real numbers, what am I doing? This is all the possible linear combinations of the column vectors of A. So this is equal to the span, it equals the span of v1, v2, all the way to vn, which is the same thing, exact same thing as the column space of A. So the column space of A, you could say, hey, what are all of the possible vectors, or the set of all vectors I can create by taking linear combinations of these guys, or the span of these guys? Or you can view it as, what are all of the possible values that ax can take on if x is a member of Rn? So let's think about it this way. Let's say that I were to tell you that I need to solve the equation ax is equal to, let me say, well, the convention is to write a b there, but let me put a special b there. Let me put b1. Let's say that I need to solve this equation ax is equal to b1. And then I were to tell you, let's say that I were to figure out the column space of A, and I say b1 is not a member of the column space of A. Then what does that tell me? That tells me that this right here can never take on the value b1, right? Because all of the values that this can take on is the column space of A. So if b1 is not in this, it means that this cannot take on the value of b1. So this would imply that this equation we're trying to set up, ax is equal to b1, has no solution. If it had a solution, if it had some solution, so let's say that ax equals b2. So let's say ax equals b2 has at least one solution. What does this mean? Well, that means that this, for a particular x, or maybe for many different x's, you can definitely achieve this value, right? For there are some x's that when you multiply it by a, you definitely are able to get this value. So this implies that b2 is definitely a member of the column space of A. Some of this stuff, on some level, it's almost obvious. This comes out of the definition of the column space. The column space is all of the linear combinations of the column vectors, which another interpretation is all of the values that AX can take on. So if I try to set AX to some value that it can't take on, clearly I'm not going to have some solution. If I set AX, if I am able to find a solution, if I am able to find some x value where AX is equal to B2, then B2 definitely is one of the values that AX can take on. Anyway, I think I'll leave you there now that you have at least a kind of abstract understanding of what a column space is. In the next couple of videos, I'm going to try to bring everything together, what we know about column spaces and null spaces and whatever else, to kind of understand a matrix and a matrix vector product from every possible direction.